Oh, I see.
Is
Okay.
it mine?
I think it's fine.
Yeah, if you close to it, that's the mic.
Okay, yeah. Good morning, everyone. And I think it's really nice to see all the familiar faces, our alumni. And mostly it's really nice to organize this conference. It's part of Moshmi's Vidushi Fellowship. She has got this, it's sponsored by through her fellowship. And yeah, I think we have wonderful speakers, experts in the audience. And they're also really a good human beings, all of these, the experts, like we have that and many others, like yeah, Ravi. So they are all young, it's a young, really a young crowd, really nice to see. So I think the young students should all make best use of this conference, interact with them. They are really fantastic people. I think it's I think it will be wonderful. I am missing it, like because yeah. So welcome everyone, and I hope you will have a good time here. Yeah, I'm Sivarani, by the way. Yeah, I think for others, yes. So hopefully you will have a fun time at IIA. Enjoy the ambience. There is a big campus. We have swallowed some campus nearby. So the campus is fantastic. You can walk around and talk to everybody and enjoy your meeting. Yeah, thanks, Moshini, for that.
Okay, so this meeting is organized by me and Sudhanshu, and it has been supported. It is being supported by DST Vidushi Fellowship. Okay, and so I'm so happy to see you all. I hope some more are also coming. We have a packed schedule. We have talks, and the talks will end at 11 o'clock today because there is a meeting by DST to discuss all the national optical facilities that are being developed and which has been mentioned in Parliament. So please join us for that small breakout session, which will be in the auditorium in that building. Okay. So after that breakout session, we'll all resume back here and have the further talks. Now, if you look at the schedule in the afternoon, so after I think 2:33, we are having some hands-on training sessions. Now, these, you cannot learn news or TNG just, 1 hour, but it will be a kind of an introduction how to use these tools, because many of you are young PhD students. So that is the aim, not just to have talks, and I know talks can become boring, but also to have some hands-on sessions. And we have very good experts here. We have Chandan, Amruta, Saili, who will be doing the optical part. We have Soumavo and Sandeep, who will show us TNG simulations. So please do stay for that. Tonight also we have the dinner at 7 o'clock. Okay, and that will be in the ICNAP lounge over there. So please all of you come for that. It will be a good dinner. Okay, I will stop now and let Preeti take over. Let me introduce the speaker. Professor Preeti Kharb is from NCRA TIFR, and she's an expert on radio continuum from Seaford Galaxies, liners, and she will tell us more.
Is there a mic?
I was ask, is it a timer? There's no timer. I just tell you.
Okay, I'll manage.
Yeah.
All right, good morning, everybody. So, really gives me a lot of happiness to actually give this talk here, and especially in a meeting which Moshmi is organizing, because I think this work actually started, and it was an idea that came from Moshmi. And so it's now been 10 years of these observations, and I'm going to there are a lot of very interesting results that have come out in these 10 years of these observations, and I'll flash. Is it?
There's no point.
There's no point. Okay, fine. Yeah. I'll dwell a little bit on the interesting results that have come out from this work. And of course, Smita Subramaniam is also here. She is the one who's kind of helped us with the emission line analysis. And so let's just get into this now. Which one goes up and down? Like this? Okay. Yeah. All right. So this is my only introductory slide to kind of set the stage and also define a couple of the things, couple of the terms that we use in the rest of the talk. So CFERTs and liners. Liners are basically acronyms for low ionization nuclear emission line region galaxies. And so these CFERTs and liners are basically just distinguished by the spectra. And liners have more low ionization lines, which are more prominent compared to the CFERT galaxies. So they're very similar in that respect. And CFERTs and liner galaxies actually form the more than 80% of they form more than 80% of the active galactic nuclei in the nearby universe. Okay, so that is what also makes them interesting to study. And type 1 and type 2 CFERT galaxies, which I will also come to in the following slides, are basically by their spectra. And in type 1 emission lines and type 2 galaxies or type 2 AGN are the ones which have narrow emission lines only. And to explain this difference in CFERT galaxies and liners, this idea of this kind of cartoon has come up for the central engine, which requires that there is some obscuration hiding the broadline region of these galaxies, so you can produce both these type of spectra. So this is type 1, type 2 has to be introduced here, and also this opening angle of this dusty tori is expected to be around 45 to 50 degrees, and that number will become important in the subsequent slides. The other thing to point out is that even though, these are the most prevalent active galactic nuclei in the nearby universe, but their radio emission is actually not very impressive. It's first of all, the extent of these outflows in the CFERT galaxies is very small. It doesn't usually go beyond a few kiloparsecs, and that is kind of shown here in this galaxy. So the spiral galaxy is here, and the radio outflow is only to here. So typically hundreds of parsecs to a few kiloparsecs. So, so that is the introduction setup. And the main point I want to mention here is that CFERT galaxies, the radio emission is not really still settled. There is still debate about whether this radio emission is coming from the active galactic nucleus or it's coming from stars or nuclear star clusters or the galactic disk stars, etc. So that origin of that radio emission is also debated. Okay, so now I'll come to our project, which I think some of you have heard these talks before as well. And we've just finished winding up this project this year. The paper just got accepted like a couple months ago. And this is 10 years of work. And I think a lot of very interesting and unexpected results actually came up, which when we started, we were looking for something else. And then we have, of course, found, the complexities of this AGM. So we started in, actually the first observations were 2013. And I was at IAA then. And then Moshmi came up with this idea that we should look at these particular very peculiar galaxies called double-peaked, we call them double-peaked, but these are peculiar in the sense that when you look at the SDSS spectrum, instead of the normal emission lines, they had double-peaked emission lines. And so we identified 9 of these galaxies that time. And so here is one example of a double-peaked H-alpha line. And so all this was fit by Smita. And the second criteria that we chose was that they should at least have been observed by one radio survey and detected in them. And that was the VLBA first survey. So we started with these 9 galaxies and we were looking for binary black holes. So the idea was that if there are binary black holes, and I showed you the cartoon in the previous slide, right? So each of those black holes will have their narrow line regions and broad line regions. So you will have these 2 sets of narrow line regions, which will give you these double peaks. So that was the idea. And we thought the best way to look for binary black holes is go and look at them with VLBI, so very long baseline interferometry, which is basically, I'm sure you're familiar now with the event horizon telescope results and all. That's a VLBI array. So high resolution radio, you need to do VLBI. And so we thought, let's go look at these galaxies with VLBI. Let's see if we see two black holes or two radio cores, like 2-point sources. So that was the exercise. So we carried out these VLBA observations at 2 frequencies, and the time between. So now first, of course, we started with this 9, kind of a pilot study. Then we actually got second epoch observations as well. And so the time between the first epoch and the second epoch was almost like a half a decade to a full decade. Okay. And so let me show you what those galaxies were. And I think, keeping in mind the conference, I will also try to tell you about the connection to galactic mergers. So these are like 6 super galaxies that we had in our sample. And so they look like nice normal spiral galaxies. Some of them may even show some signatures of galaxy mergers, but not very prominently. But the 3 liner galaxies that we had in our sample were actually, they were all showing some peculiarities which looked like related to mergers. So these were the 3 galaxies. All 3 of them had 2 optical nuclei. So in this one, you can see very clearly. Others are not so clearly because they're a little bit closer to each other. So these were the galaxies we had chosen. And since I mentioned that they were all, one of the criteria was that they should have been detected in the VLA first survey. So these are the VLA first images, contours superimposed on those images, optical images. And you see the green contours that you see are the radio emissions from these galaxies, which is nothing very spectacular. You see point sources, they are very low in flux density, very weak radio sources were present in these galaxies. But when we looked at them with VLBI, we started seeing very interesting results. For example, what looked like jets. And so this is one example of one of the VLBI images of one of the galaxies called Kharb A, Kharb 434. I forgot to mention what Kharb was. So Kharb was a sample we chose, which was actually, it came from KITFI. And this was a sample of emission line galaxies. Okay, so that was the sample that Washington has suggested that we should look at. And so in the very first epoch of observations, we already found that more than 60% seem to have some kind of jet-like structures. They were not very prominent core-jet structures that you see, for example, in blazars and quasars, but they look like compact component and then some kind of elongated structure. So this is one of those. Okay, the second, the interesting thing was that in the second epoch of observations, which was carried out 5 years later, almost all of them, 100% of them showed jets. In fact, some of the sources which we didn't find jets in the first epoch showed jets in the second epoch. So that was very interesting. So obviously these structures are very dynamic, and sensitivity of course matters, but also they're changing very fast over these 5 years. They change. So we could see the jet emission in all of them in the second epoch. And so the question here is, was this a selection effect in the sense, did we choose these galaxies in such a way that they were then being detected with VLBI? So that was one question. So another very interesting thing that we did was we assumed that these jets are, let's say, like, laser jets. And then usually you assume that the jets are relativistically moving. And because of this relativistic motion, you will have brightness differences between the approaching jet and the receding jet because of special theory of relativity relations. So we use that, we assume that that is the case. And then we assume, since we didn't have any idea about the inclination of these galaxies, you need both the speed of the jet and the inclination of the jet to kind of make this calculation. Since we didn't have inclination, we knew that they were all type 2 galaxies. So we assumed that the orientation has to be more than 50 degrees, right? Because I told you half opening angle of the torus was 50. So assuming that, we derived some speeds for these jets, and they were turning out to be whatever, 0.003 times speed of light to 0.75 c, which is quite high. Okay. Now, after 5 to 10 years, when we looked at them, first of all, one very interesting thing was that all the things that we saw, which looked very, they looked almost like noise peaks, but those noise peaks stayed. So the core jet, so-called core jet structures persisted over 5 to 10 years. So that gave us a lot of confidence that this is real. And so this is the same source in January 2018 and November 2022. So you see the similar features, but there are some differences. So the so-called core now seems to have some extra mission, perpendicular to it, etc. So those were also very interesting. But most interestingly was that at least 2 sources we found that the jets seem to be moving at close to speeds of light. Okay, so see, when we did the jet to counter jet brightness ratios, we were making a lot of assumptions like what is the inclination of the jet, etc. But now, since we had 2 epochs, we could actually trace jet motion. So we could actually get jet speeds. And when we got the jet speeds, we found, for example, in this galaxy, the jet naught, so this is the core and this is the jet or VLBA scales. It was moving at 1.6 times the speed of light. So that's superluminal motion, radiant speed of light, which is telling you that the jets are moving fast, but obviously not quicker than the speed of light, but close to it. And this is the second source, KISAR 102, which in the first epoch looked like it had 2 components, and we were very excited, wondering if these 2 components were actually 2 black holes. But in the second epoch, we found that there is motion. So, in fact, this A and B components were separating with a speed of 1.05 speed of light. So also kind of almost superluminal, but very fast basically. Okay, so at least 2 sources we found that jets were moving fast. Now that was the first epoch we had kind of results suggesting that there could be Doppler boosting. You can remove my bag and sit here also. Was suggesting that the jets could be relativistic. In the second epoch, there was some actual proof of that, there's actual speeds being almost superluminal. The second very interesting result that came from this study was when we looked at both the VLBA data and the emission line data, and this is where Smita's contributions came in, and they were very important because we found that somehow this this very wimpy looking jet was actually probably was influencing the gas clouds around it. And so we tried some emission line modeling, and the best model that we found to explain the emission line ratios, etc., was called the shock plus precursor model, which is telling you that it's not the actual shocks from the end of the jets which are kind of impacting the gas clouds, but rather some kind of photoionized material through the shock gas, through the shock jet, which then impacts and photoionizes material far away from the AGM. Okay, and so this kind of model was working in our to explain the line ratios. So we suggested that maybe a model like this is actually taking place in these galaxies, that you have a fast jet, center of the jet, which you see in the VLBA images, but the emission line gas clouds are probably in some kind of a slower outflow around them, or the gas clouds are being impacted in a transverse direction to the jet motion itself. So this is also something that comes in from simulations, etc., that you have the jet impacts the medium around it, even in the transverse direction, not just the head of the jet. Okay, and so this idea came because, of course, the line separations the double peak separations were actually only around a few 100 kilometers per second, whereas the jet speeds are the jet speeds are at least 100 times higher. So it's not that the jet itself is moving the gas cloud, but maybe something in the transverse direction, or some kind of a slower wider outflow. Okay, so this told us that the double peaks are much more likely to be from the jet NLR gas interaction rather than binary black hole escaping sources. And so it already tells you that this, there is some kind of signatures of Asian feedback, even in these very, very, low luminosity AGN. That's the first thing. Then we actually went ahead and also got some arc-second scale observations, VLA observations. And this was only for a fraction of the sample, not the entire sample. And here also there were very interesting results. So here, this is now the say one galaxy, KISAR 434. This is the optical light, and the black contours are the VLA emission. So now this is now arc-second scale emission. So we went from milli-arc-second parsec scale emission now to kiloparsec scale emission. So you see here, what you see here, I mean, doesn't look like anything. It doesn't look like jets. It looks like some compact core with some diffuse emission. And here is the same feature shown again. And here the color pixels are the radio spectral index. Okay, so you can see some sort of steepening, maybe from the center or this region towards this particular region. But the shape of this emission is completely amorphous. You don't see live jets, you don't see lobes that you see in AGN, you don't see any of that. But what we found was that this red arrow is actually the VLBA jet direction, which we got from our images. This seems to always, in all the sources we looked at, the VLBA jet is pointing in the same direction as the steepening of the spectral index in the VLA images. Okay, so when you looked at the VLA images, you were not sure, is it AGN, is this star formation, is it what? But the VLBA jet direction is actually telling you that the change in the spectral indices is related to the VLBA jet direction. So that was very, very encouraging. It tells you also one more thing, that the jet decollimation rather, from parsec scales to kiloparsec scales was happening between a few hundred parsecs on VLBA scale, because those we saw 100 parsec scale jets. And this extent is a few kiloparsecs. So the jet is somehow decollimating. Obviously, you don't see a jet, right? You don't see a collimated structure. So it is the decollimation is happening between, let's say, 150 parsec and 4 kiloparsec in this case. And similarly here, this is another galaxy 872. Again, you see some kind of extended emission here. Not really like a jet, not really like a lobe, just some extension. But again, the same trend is seen that the steepening in the spectral index on arcsecond scales is related to the VLBA jet direction. So here again, we could say that the jet was decollimating between 200 parsecs to 5 kiloparsecs. So we, from all this work, we were able to also see that not only do you have these maybe fast jets on small scales, we were also able to see that these small scale jets are influencing the narrowline gas clouds. It is also somehow responsible for the amorphous radio diffuse emission that you see in kiloparsec scales. So that was also very, very exciting. Now I'll come to the last part of it, which is that when we looked at the VLA images of these sources, we had also done a polarization study. So we had actually, the data was polarization sensitive, and we had data for 4 galaxies, but in only one galaxy we saw polarization. And this was Kharb 872 again. And so this is the same radio contours that you saw in the previous slide. And the red ticks here are the polarization vectors. And the lengths of these are directly proportional to the degree of polarization, fractional polarization. So the fractional polarization was very large in this galaxy, almost 30%. So this is already telling you that the magnetic fields are kind of very nicely, closely aligned. What was also interesting, so here, these are the polarization vectors. So the magnetic field in this optically thin synchrotron emission is expected to be perpendicular. So the magnetic field is in this direction and in this direction. And this was actually the direction also of this merging galaxy. There was tidal tail and this going up like that. You see something here, but there's also some tail here. And this was exactly perpendicular to that tidal tail. So this is suggesting maybe that there is some gas accretion happening between these two nuclei. So this is a galaxy in the middle of a merger, and gas is being pulled from the secondary nucleus to the primary nucleus. And in this motion is somehow compressing the gas and the magnetic fields, giving the rise to this polarization that you see. So this is actually seen in some other, not the polarization signatures, but this kind of behavior is seen in other interacting galaxies also. For example, NA6240. Okay, so so I've shown you, I think, a couple of links to galaxy mergers, but I will point that again once here in the end. Let me just summarize what we did, what I've done, what I talked about at the start. One was that when we looked at these galaxies with VLBA, we see the presence of jets in almost all of them. These jets seem to persist between epochs, but they also change in some sources. In some sources where we didn't see a jet, we saw a jet in the second epoch in the same source. In some source where we saw a jet in the first epoch, we didn't see the second epoch, etc. So there is a lot of changes are happening on these in these galaxies. The fact of this persistence of these features is telling you that these are actual jets from AGN in these super galaxies. And the fact that these rather the double peaked emission lines can be explained by the fact that these are jets interacting with the NLR gas. So now the interesting point was that the two sources that we found fast jets were actually these two liner galaxies, which are actually which are the ones with two optical nuclei. So they are definitely in some, and Kharb ones, 872 was the one that I showed you in the previous slide. So could there be a link with the fast jets and the merging activity? So we haven't really explored this phenomenon. This is something probably we want to explore, that the two fastest jets were the ones which were inside interacting galaxies. So I think that was the link I wanted to make with the workshop theme. And I'll stop here and I'm happy to take questions.
Please stand here. So I want us to about this. Please go ahead and ask some questions.
That's so rich.
These are very, very close by. So I think maybe 0.01, even less. I did tell you. So I'm saying that since we selected them on the basis of the double peak lines, and then we find that they all have jets, and then we are saying that these jets are the ones which are causing these double peak lines. So that is the selection effect. That's how we understand these results.
So I have a simple question regarding something. I think we realized that you mentioned all the galaxies have two nuclei.
Yeah, all the liners.
And maybe it's probably like they are separate, and given the storm further, probably double peak is coming from only one galaxy.
Yes.
So yeah.
Yes.
That was
Yes.
a huge selection effect in
Yeah, so exactly, that's a good point. So the double peaks are still coming from that at least in the Kharb 872, it's only one of the nucleus which is giving these double peak lines, not the second nucleus. So the SDSS fiber doesn't come, they've separated far enough that they're not coming from this one. But in the two which are very close, I don't remember now if they were actually within the SDSS fiber.
The double like one.
The double one.
Yeah.
The double may have been, I don't remember.
Yeah. That was within one fiber.
Yeah. Yeah, the one which is the closest, which you can't see, but you can see in high resolution images. It may be, but at least in Kharb 872, which was the one which has this nice fast jet and all that, the double peaks are also coming from that single optical piece.
Do you think if someone divides the samples in the sense that you come from
Correlate, huh? Yeah.
Would it be a better approach to
We should try.
There are that many deep optical images of many of these images. I think machine learning would be a good way. No? Like, for example, the HSBC survey, surveys like that, look to all the spectrum.
And so one thing is that these double peaks are in the narrow lines, no? That is another thing to remember. Yeah, so these are not broad emission lines, which I don't know how that thing works there, because the broad emission lines, sometimes people have suggested that they are binary black hole. We have picked up the narrow ones. Yeah.
So the impact is it's bad.
Yes.
Most of them things to the negative. So the silver. We also have a cloud also that we can infer the slope.
No, okay. So no. So this is actually an in-band spectral index image. I haven't seen it probably has some curve, but I haven't seen that curve. But it will still be not, it's like 1 gigahertz or something. Like this band is like only a 1 or 2 gigahertz band. It's not like, yeah, this is in band. It's 1.5 gigahertz. I think it's probably 2 gigahertz band.
And this is
bandwidth.
If you thought, if you have any map of the both the nucleus, is the spectral index map also has any signature that the direction of the synchrotron synchrotron is primarily the change direction maybe. So
you mean like this? Yeah, so here, there is nothing on the other nucleus. There's no radio emission at all, actually.
Okay.
So there's only one radio emission only associated with one of the nucleus, which is the one which is we're looking at the VLBA. That is the alpha image for that. So you were trying to say spectral index and the optical nucleus signatures. Yeah, we don't have anything like that, actually. Yeah, that'd be interesting. I wonder how there was the one which is very close to each other. I should look at that to see if there is. I didn't see anything, but I could look.
Any more questions at the back?
So this diffuse emission is happening like portions or is it in the plane of the galaxy? Like I didn't understand.
Say that again. The diffuse emission, is it in the plane? You mean to say you're trying to understand if this kind of S-shaped thing is coming from the. I think there is some optical emission associated also around. There's some kind of a curve there as well. It's not clearly one-to-one, but I think, yeah, I don't know if some of it is galactic. I mean, I'm thinking that the alpha that we see here, which is trustworthy, is only in the center anyway. We're not seeing anything in the spiral arms, so-called spiral arms. I mean, there may be a contribution. I don't know.
There's one question on Zoom.
Yeah.
I'll just read it out. It's
Yeah.
from Shravya, who says that you mentioned that the radio emission changed for some sources over the span of 45 years. And so she was wondering whether you also have to repeat observations for the optical spectra over similar timescales, and if so, do you see any variability?
Oh, okay. Okay, yeah, that's an excellent question. We are just relying on SDSS spectra, and yeah, I mean, it may be a good exercise to also see the spectra changing, the
Yeah,
optical spectra.
yeah, that would be really good.
Yeah, we haven't looked, but yeah, that is probably worth looking into.
Okay. So if there are no more questions, then let's thank.
Thank you.
So our next speaker is Soumavo Ghosh, who is the faculty at IIT Indore, and we will just can you hold?
Yes, well.
Yes. Artist. Professor.
Good morning, everyone. First of all, thanks, Maushami and Sudhanshu, for this generous invitation. It's always nice to be back in Bangalore. So today I'll talk about like the galaxy mergers and its dynamical effect on to promote or to destroy the bar. So that's why this double showed the title there. So I'll talk about how these galactic mergers are likely to impact something called like the bar that we encountered in these galaxies. Okay, so just to set the stage, so let me start with like the good old what is called like the galaxy classification scheme, which is like done by several years back by Hubble, but still good to give you a basic understanding of how the galaxy classifications are done. And this is called like the teaming fog diagram. So on the very right hand side you have the irregular galaxies, which are of course the morphology is irregular, they are lower mass galaxies, and then you have these galaxies over here. Then at the junction you have the lenticulars or the A0 galaxies, and on the very left hand side you have the very massive elliptical galaxies. And the conjecture is that the galaxy actually starts its career from the irregular galaxies, and they grow in terms of mass and size by merging with other galaxies, and that's how they evolve throughout this age. Of course, this is one conjecture. So another way of putting things like here. So if you see these galaxies on the top left images, so these are the galaxies that are relatively higher redshift galaxies, And as it is like very evident from their morphology, they are very irregularly shaped, they are clumpy in nature, and they are this is more puffed up in the vertical direction. Now, on the other hand, if you see the galaxies that we encountered in our local universe, they look very nice, smooth, and they have these beautiful structures which are called the bars and the spirals, right? Now the question remains how to go from here to here, right? And again, there are some studies, of course, I'll come to that, and then the conjecture or the idea is from going here to here, the flyby encounters and the mergers and the gas accretion play a pivotal role from transforming galaxies from this to this. Of course, there are some internal processes which are also involved. For example, star formation, stellar feedback, and Barrett spiral. But since this is a conference, the workshop is all galaxy mergers, so I'm not going to that. So that's all. Okay. So of course, here I have shown so far all the galaxy mergers and all these things. So these are conjectures, right? So if you are skeptical, you might think ask that what is the proof or what is the argument that galaxies indeed will go through some interaction or the merge, right? So let's have a theoretical perspective. So there are a few time scales. Those are very interesting. First of all, the cluster crossing time scale. Suppose you have an extended object, and then you want to calculate the time, which is a particle or the body will require to travel from one end to another end throughout the time. Now, if you take a typical cluster, so the cluster size is of the order of the 1 megaparsec, and the typical velocities between the galaxies are of 1,000 kilometers per second. And then if you put the number, so this is going around roughly a billion, right? Now the question is, of course, the galaxies, whether they are the collision rays or not. Suppose in a cluster of galaxies, there are many galaxies. So the question is whether they interact or they collide. Of course, this is the traditional way to not only in astrophysics, so in physics also what we call calculate the collision times, right? So this is nothing over 1 over n sigma and b, not to confuse with this sigma and this sigma. This sigma is basically collision or cross section, right? And this is the typical velocity, and this is the number. Now let's put in some representative numbers. So the relative velocities between two galaxies in the X cluster are typically 500 kilometers per second. The average galaxy radius you can take in 50 kbc, and then of course the collision or cross section will be like this. And then of course for calculating n, you can also assume that there are of the order of 100 galaxies within a radius of 1 megaparsec. And then if you put in the numbers and compute, and then the collision time scale comes out to be few times 10 to the power 9 billion. So this is much less than the age of the universe. So that sort of gives you argument that the galaxies indeed collide or they interact, unlike the stars in a typical these galaxies which are collisionless system. But if you consider the galaxies in a cluster and all these things, they certainly collide or interact. Of course, this is some back of the envelope calculation. Even if it doesn't convince you, this will. So these are the pictures actually taken from the HST telescope, and these are very beautiful systems of interacting galaxies, and they are actually it's interaction happening, and we are lucky actually catch them on the hand, right? And in each of these cases, you can see there are multiple galaxies which are going through some tidal interactions, right? Of course, HST is become old. Now we have better images from JWST. So this is again R42, which is system of again interacting galaxies. So you have this elliptical galaxy NGC 237, and then of course this is the distorted one and closely resembles to penguin or something. So anyway, this is this galaxy, and you can clearly see these galaxies are interacting. So of course, before I delve into the nitty-gritty of this talk, so let me clarify a few terms, what sometimes I tell interaction, sometimes I tell merger. So the merger is nothing but the extreme case of interaction. Interaction is when you have just one tidal encounter, when they exert tidal forces. But on the extreme case, the satellite of the companion galaxy actually might fall into the host galaxy, and then they merge. So that's the merger is basically you can think of an extreme case of an interaction. Now, depending on we different properties, we have several types of mergers. First of all, the mass ratio of the participating galaxies. If the mass ratio of these participating galaxies are like above 1:5, we call it normally a major merger, and if it is below 1:5, then we call it like a minor. And of course, like the gas content also like has something to do with this merger. So if the participating galaxies have gas rich, then we call like the mergers as wet merger. And if like the participating galaxies are like gas poor, then we call it like dry merger. And of course, as you can also like imagine, like the orbital configuration also matters. Like it can happen like the satellite is coming in the same direction as the rotation of the other galaxy, and it can also come in the other way. So depending on that, you can have like direct or prograde, where like the satellite is coming exactly at the direction of the rotation of the other galaxy, and the other case is retrograde, where it is coming in the opposite direction. So these are like a few like classification which will come handy in the later part of the talk. So I just wanted to like tell like very explicitly over this. Now there have been like decades of starting to understand like what are the dynamical impact of these galaxy interactions and the mergers on the galaxies, right? Of course, here I'm like mostly like focusing on the dynamical part. So of course, but this is not like the end of the like the list. Of course, like there will be many more, and I'm hoping that more to hear from like during this like this workshop. So just to like give you like very like brief like overview of what it does to the galaxy, it can actually result in this sort of morphology, and then can also have like the wandering of the centers, we call like sloshing. It can also like increase the random motion of the stars in the within the galaxy, we call it like disk gating, and it can also like puff off like the disk in the vertical direction, we call it like part of the thickening of the disk. Also, it can actually like slow down like the galaxy in the sense like the rotational circular velocity can like increase in the post-merger remnant. It can in some cases it can also enhance like the star formation. It can also like excite like some of the morphological and kinematic lopsidedness, some distortion like in the morphology and the kinematics of the galaxy. But today is like I'm focusing on like what is basically impact in triggering an n equal to 2 bar in the host galaxy. Now, of course, like I see like a mixed crowd of young and like experts. So, like in case like you are like hearing the bar like the from bar for the first time. So this is like I essentially mean. So this is like the some elongated like central structures that we encountered in these galaxies, and these are called the bars. And just to give you a number, like more than 2/3 of the spiral galaxies in the local universe are actually bar. And when I say bar, essentially I mean this. Not probably like this kind of thing where we probably like ended up yesterday for the match. So like how about like the past studies of like impact on the interactions on this formation of path, right? So there are like first like let's talk about like from the observational point of view. So there are like past observational study that actually like counted like how many barred galaxies are there in a cluster environment, and as compared to like the other like field environment. And they showed that these are the studies like they are targeted in the R2 and the Homer cluster, and they showed that like there's an increased bar fraction in this cluster environment. So then you can actually argue like in the cluster environment, just now like we actually saw like in the cluster of like galaxies they interact or like the merge. So you can also like say that okay, so this relative increasing of this like the bar fraction could be due to the enhanced like tidal interaction that you see in the galaxy clusters. However, just to like keep in mind that of course it's not very straightforward. Like the bar triggering of the bar by this galaxy interaction also depends on the galaxy's mass and also like its ability to maintain a hold this component against the heat. Right. Of course, this is from the theoretical perspective. Of course, there are decades of study like theoretical study by simulations, and they actually like support like this triggering of n equal to bar by tidal interactions. And I have listed here a few studies. Of course, there are many more. But you have to remember that the properties of the resultant bar actually like depends on the presence of the interstellar gas, mass ratio of the galaxy, and the relative phase of the bar and the companion at the very center passage. Of course, this is fine, but again, like you see, like here, like I am only talking about the interaction, right? Not the merge. So the natural question is, okay, we know like in the tidal interaction they trigger bar, even some like some other factors. But like what happens with like if the satellite actually merges with the host gas? That means if you then consider the extreme cases of the interaction. That was still not known, and that's what what came into picture when we actually studied the effect of these marches on the bars. Of course, as I mentioned, the major markers, where the mass ratio is above 1:5, they are found to be very catastrophic, and it is very challenging to maintain a disk-like structure. So it's futile to ask what happens to a bar if there's a major marker. So instead we focus on all the minor markers. And here we use the database of the simulations, which is called the GALMAR, which actually provides medium resolution galaxy marker simulations, and where we have a lot of variations in terms of the mass model, in terms of the geometry configuration, in terms of the Hubble type, because we have galaxies from elliptical to very type galaxies. So given the Hubble type, so the galaxy can be modeled as a central bulge. You have a stellar disk and a gas disk, and the whole system is embedded in a. So how this is so let me show how this one simulation actually looks, where you have 1:10 minor markers, that means the mass ratio is 1:10. And initially we put the satellite as some very distant. So here in this case we have put the satellite at 100 kpc apart, and then we let it go and let's see how it happens. So these are the spatial surface density, and you can see at some point the galaxy actually comes so this is called the pericenter passages, and you can see here above we have shown how the distance between these two galaxies actually vary as a function of time. So at some point there will be closer approach, this is called the first pericenter. Then of course it goes through various ways. It doesn't plunge through because of the conservation of angular momentum. So it's the circles, and then ultimately actually become the distance becomes that means the marker is common. And then of course then the host and the satellite lost their individual identity, and what they become what we call the post-marker remnant. So this is one prograde model where of course the satellite is coming exactly in the direction of the rotation of the host galaxy. So let's see another model where the galaxy is coming in the opposite direction. And of course the main it is not very evident, but here of course here the merger happens at a very late time. So you have that's to show the kind of variety these galaxy simulations actually offer you to study under different what happens to the bar under different geometric configurations. So if you have this is the prograde model. So if you have a close look at the central region of the bar, because that's where the bar is located. So you can see initially you have a very elongated structure, that is the bar. We have already pre-existing bar, and then of course at different times the merger happens, and this is at the end product. And you can see this if you have a careful look, the contours are not very elongated, right? So that sort of hints maybe the bar is not there, or maybe it is weakened, right? But these are only visual inspection, so you need more one. So exactly what we did, what an observer would have done, we created the mock light images from these simulations at the beginning and the end of the simulations, and then we extracted the radial light profile, and we tried to model with decompose with with different components. First of all, we have a disk, which is the exponential profile. Then we have a bulge, and if these two components are not sufficient, that means if the residuals are quite significant, then you also added another third component, which is the bar, and both the bulges and the bars are actually modeled with the subsequent, but subsequent tests can be different, right? So that's what we did here. So if you see at the top level, this is the radial surface density profile, and then there's a bulge, there's a bar, and this is the disk, and this is the total, right? Fine. There is also something we call the ellipticity of the profile. This is nothing but the axial ratio 1 minus axial ratio. That's the ratio of the major axis and minor axis. So in this case, at the beginning, you can clearly see there's a nice peak over here, and this is the position angle of these the contours, and you can see they are constant moving in the central. So these are classic actually signatures of existence of a bar that you can derive from column. Now let's look at what happens at the end, right? So here you can see if you just fit a bulge and the disk, then the residuals are sort of fine. So you don't need a second component. And again, if you see the peak in the ellipticity profile at decrease quite a lot, and there's of course there's position angles are not as constant as they were in the initial case. So then we argued like, of course, like, from the photometric, like, argument that we can say like, because of this merger, this like the bar has destroyed in this point, right? But again, like, since we are dealing with like, simulation, so we are playing God over here. So we know the intrinsic, like, particle, like information. So we can do actually a better job by doing the Fourier analysis where we actually like, suppose this is a disk and they have a bar. Then you put like, the radial concentric annuli and then you compute the corresponding Fourier amplitude and the phase angle. And then the characteristics of the bar is nothing but like, you have a peak in the A2 profile along with the constant phi2. This is quite important. And of course, like, if you have a strong bar, then also it gives you a relatively like lower but a non-zero peak in the A4 profile as well. Where A4 is nothing but the amplitude of the ML Fourier mode, right? So again, that's what we did. So the black lines are actually the bar phase at the initial time. So the solid line is m equal to 2 and the dotted line is m equal to 4. Then you can clearly see there's a peak. There's also a peak in the m equal to 4. That's what I tells you. There's a bar. And then if you see the inset, like, these are the blue lines, and I will purposely like sort of like, change, but even if you see carefully the numbers, that the peak has got reduced like, below 0.2. Again, there's a decrease in the A4 profile as well. So that again sort of tells you like, there's a no bar, right? And of course, you can like, define the strength of a bar at a certain time, and this is nothing but the peak value of this at a given like, time. What is the peak value of this equal to Fourier amplitude? And then we actually computed like, for this model, how the strength of the bar is actually like, like varying as a function of time. So the black lines is like, before the merger happens, and the red is after the merger happens. And this magenta vertical, like, arrows are basically showing what is the pericenter. So you see a very nice trend that whenever there's a pericenter passage, there's a like, transient, like, increase in the bar strength, which is consistent with the earlier work that the tidal interaction will like, either excite a bar or like, make the existing bar more stronger. Again, see like, there's a nice sort of like the second pericenter. However, if you see like, when the merger happens, then like, all like the steadily increase. And often in our theoretical study, we use like, some sort of like, empirical definition that if the strength of the bar is less than 0.2, we do not regard this as a bar. So if you like, impose those like, operational definition, then you can claim that, in this like, model, the bar has destroyed because of this galaxy model. We of course like, this is not the only case. So in this study, we have actually like, studied around like, 14 or 20, like 15 like, models. And these are again like the strength of the bar evolution with time for different model. And here, like everywhere, we see the same thing. Whenever there's a pericenter passage, there's a transient increase in bar growth, like a bar strength. And then of course, like, when the merger happens and you have sufficient time to actually like, adjust, then the bar length and the bar strength actually decreases quite steadily. In some cases, it can completely vanish. In some cases, it can be weakened. And just to like, tell you like, there's no like, magic. So there are of course like, some like, physics going on. So this is like, one thing that can actually weaken a bar, that if somehow you can accumulate more and more mass in the central region, that sort of like, disturbs the stellar orbits, or what is called like X1 orbits, that serves as the backbone of the bar. So they get destroyed, and that's exactly what is happening. So you can see these cyan points, those are the star particles. You can imagine those are the star particles coming from the satellite, and there's like a steady accumulation of these stellar particles, like, as like, there's a merger, and then if you let it go for a long time. So this is like, one like, physics going behind this weakening of the bar. And then of course another thing is like the angular momentum exchange. Of course, like, we know like the bar can be thought as a like, wave of negative angular momentum. So in order to bar to grow, you have to extract the angular momentum, and that's how the bar grows. You can also think of it in a reverse way. If you can somehow inject the angular momentum in the central part, then the bar actually gets weakened, and that's exactly what is happening over here. Sorry. So you can see here, so this is like the blue line is like, for the satellite plus host galaxy, how this like the angular momentum is changing in the central region. And you can see there's a like, bit of angular injection of angular momentum because of this satellite particles, they actually like, bring the angular momentum in the central region, and that's how like the bar gets like, weakened and in some cases destroys. So that sort of like, brings to the take home message. So a minor matter can actually like substantially weaken the bar, although a tidal interaction can trigger the bar. So that's why it's a double shot. And of course, like, the mass accumulation and the gain in the angular momentum plays a key role in weakening the bar or destroying the bar. So these are the 2 points I hope to cover because of like the time constraint, what we have not talked about. So also like the efficiency of this accumulation, like of the mass and the angular momentum, critically depend on the orbital parameter Hubble type of the satellite, because you can imagine that it's always easier to break a spherical object than a disc-like structure. That's why like the morphology of the satellite comes into the picture, and that can also like explain like the art of like the strong bars in a RV like this guys. So with that, I'll stop here and I'll be happy to take questions. Next.
So, we checked that this was a case, in case of a small bar, you check for wider methods. So, we check the case of the big bar, then it can be the bar to get something.
Yeah, that can happen. So that's exactly what it said.
Yeah. So, and this thing like temporary, like bars and easy, this is happening only when it is in the case of switch, right?
Yes, when there's a pericenter passage, so there's a tidal interaction, and there's sort of like, so this pericenter passage. So I think like, so this is actually quite like an impulsive like, force. Just comes in and goes around and just like, looking at the.
Get to the past and
Yeah, so it's like, so 0.5, some mega years. Okay. So those are like, you can also like, model it as a, like, impulsive force, right? So it comes like, very.
So, they will always basic picture of like that.
Yes, of course, but it depends also like, so probably what you are trying to ask, whether we can detect. The detectability, like, relies on how much longer this, like, the feature actually persists. If it is very like in a small scale, you are likely to miss.
So, how much sensitive these chemical is with the ratio of the mass surfaces?
Well, that's a good question. So, of course, you can see like, these are 1:10 mergers. So, we had some like, not included in the paper. We have like, included some 1:20 like, mass ratio. And of course, you can see like it depends on like the tidal interaction and also how much like, mass you are bringing. So, if your mass ratio goes down, then these sort of effects also become like, tries to be like, less and less. So, it depends on the mass. Sorry, I didn't get you first. So you mean the merging time scale? Okay, so for these four-grade merger, actually like, these merges around like, 1.5 gig a year after we start the simulation. So it takes around like, 1.5 gig a year to merge. However, for these galaxies, it takes sort of like, roughly 2.7 gig a year to merge. And it depends a lot on like the orbital configuration, what is the initial velocity you give, what is the initial momentum you give. So it depends a lot on that. For similar for?
the final.
Yes, of course, like the general trend is there, of course. So, like, whenever there's a pericenter passage, there's a like, a transient increase in the bar strength, and when there's a merger, and then there's a weakening of the bar. That trend is, of course, there, but on which time scale it will be like effective to this particular like model, that depends on like all these like the simulation setup. But the result, right, overall trend is robust.
Do you also include the effects of dynamical friction?
Yeah, it's already there. It's already there.
Is that right?
Yes, so these are like actually the GSA, so they have like 10% gas. Yeah, so these are also the same.
Nice question. I have like sometime in literature we define laser merger as it is like
These are 1:10, so they are safely minor mergers.
no, but so I just want to know what can we improve that.
I mean, there is no like, there is like nothing written on the like in a stone that okay, this is the case. This is again like normally 1:1, 1:2, 1:4. You can still call it a major merger. And maybe like in one, it's not hard and fast, but it's all depends on like the what community believes and like the community standards practice.
One last question.
Actually, I have a similar question with dry myself. So, in case of dry myself, mostly I put it plus right?
But we already have a classical bulge in the.
Back myself.
Okay. So of course, like here in this paper, our like focus was on mostly on the parts, but not but as you said, like
Time again from the distant possibly
right. Yeah, but just to like respond to the question, we have not frankly speaking, I mean, honestly, like we have not actually looked at the very late margins. So, but yeah, that's a valid question.
Maybe afterwards you can discuss.
Yeah, sure.
Because we're running a bit late.
Yes, yes.
So thank you for go ahead. Well, our next speaker is Dr. Prajwel Joseph, who recently graduated. He's a UBIT expert.
But then I'm also interested in galaxy evolution and alien feedback. So this particular work that I'm going to show you uses UBIT data, and it is also related to the theme of this workshop. It's the post-merger galaxy, so you have already heard about Prajwel from Ghosh, the jets from Preeti. So I'll tell you about how Jet has shaped this particular post-merger galaxy. Formation in Centaurus A. Just to give you a brief overview, what is meant by star formation? Star formation happens from molecular collapse, they form stars, and then they go to every cell of life. If you supernova happens in some cases, then all that goes back to the interstellar medium, and this goes again the cycle repeats. And key processes that are affecting it are turbulence, magnetic field, self-gravity, as you all know. And the AGN can have a profound effect on this particular process because AGN can produce copious amounts of energy through accretion. And if you make some rough calculation, you would like to do this. Energy released by an accreting supermassive black hole can be almost 100 times more than the binding energy of a galaxy itself. So some of this energy gets imparted on the gas content that can profoundly affect how the galaxy works. Now, AGN feedback does not operate in one single way. There are two categories mainly, which is the radiative feedback, and where it lots of energetic photons produced, and there is mechanical mode as well, which is you can think of it as where the jet occurs. That there are energetic particles, and one difference is that radiating mode can be more or less affecting the whole radially. isotope of the galaxy, but in mechanical mode, it is more or less coordinated. And both the jet or outflow generated by this both these modes can suppress or trigger star formation in galaxies. So now observing star formation in nearby AGN host galaxies in high angular resolution can provide insights into how AGN feedback affects these galaxies. And of course, one good way of observing star formation in nearby galaxies is using ultraviolet imaging data. And why? Because short-lived and UV bright OBA type stars produce lots of UV light. And using them, you can trace wherever the younger stellar populations are present. But there is, of course, a caveat with respect to any method, which is that UV radiation gets highly attenuated by dust. So you need to keep that in mind whenever you are using UV data to probe star formation. Okay. So that's why you just cannot restrict yourself to UV data alone. You need a multi-wavelength approach. Because AGN activity can be traced in almost all bands of the electromagnetic spectrum. And as I said, the dust distribution in a galaxy is important because UV light is attenuated by dust. And you also need to identify and remove foreground sources, which you may think as star forming regions in the galaxy that we're studying. So with that, let me get into our source. This is Centaurus A. It underwent a recent merger. And one very interesting thing about this galaxy is that it is the nearest active galaxy to Jupiter. And it has ongoing star formation in the disk. But we are not going to look at the disk. We are going to look somewhere here. And the current jet activity you can see it is traced by this emission. This I think this blue emission is from X-ray, and that is this is right in infrared. As you can see, the current jet is only to here, but then we are going to look somewhere here as So again, that was a optical X-ray composite, but this is just the UV image alone. Again, you can see the disk of the galaxy, and there are lots of structures that you can see in the northern region of this galaxy. And now we are just going to understand what is going on in here. So you can see some ribbons, some pole-like structures, and it is very diverse. It's not very, it's complex. So our idea was to understand what exactly is going on in this northern region of this particular galaxy with respect to how the AGN jet shapes it. So we are just going to focus on that particular region around the northern region. As I said, this is the region that we are going to look at it. This is a composite of 3 separate pointings of UVAT, but we are just going to look at this region first to understand what is going on there. So one more thing, this galaxy has a huge structure in radio. So as you can see, what is observed by UVAT is just this tiny region, and you can see the radio emission traced by radio emission from this Centaurus A galaxy is much larger. But we are not going to go into all this now. We are just going to look at this particular small region. But I'm going to do this a lot in this particular thing. I'm going to zoom in and zoom out because we are going to look at Hubble Space Telescope data as well. So we are going to even further go zoom in on this. So bear with me when I zoom in. So first thing is that we already noticed that there are point-like and diffuse emission. And this particular square-shaped box, we call it as the northern star-forming region. That is just our terminology. And we again classified that particular box into 2 regions. One is outer region marked by this So let us look at what's going on here. So again, just to, because I'm going to do a lot of zooming in and zooming out, I want you to follow me. That's why I'm showing you many images. So this is again the northern star forming region, this is the outer region, and this is inner region. So first, our idea is that we need to understand how the jet activity brought this galaxy. As I said, the present jet activity is only up to here. As I showed you in the first this image, the present jet activity is only traced up to here. But there are radio emission, spanning some 8 degrees in the sky. So what is going on here? So in order to understand that, what we did was we looked at Parkes radio telescope 6.3 centimeter data as well as one system vertical array 185 megahertz data. And then in the literature, it is said that there are some radio bubbles and X-ray bubbles in this particular region, and which is thought to be created by a jet interacting with the gas cloud there. So all we did was we just connected from the center of the galaxy to the center of that particular radio emission. And then we assumed that this is a potential path of the past jet activity. We call it past jet activity because the present jet activity is only up to here. But we wanted to know how the star forming regions and the things that we observe there is shaped by if present or past jet activity. So we now are going to assume that this is the potential path of the past jet activity. And look, there is a lot of detective work involved because we are seeing the currency and then we are trying to make out what happened. So we will assume that this is the past jet activity. And with that idea in mind, we are going to now look at what happened in the outer region, this region. So this is the outer region, as I said, which is a lot of images because I'm going to zoom in. This is the outer region. This is the outer region. And this is that particular part of the past jet activity. And one thing that you can see is that in this image, I'm showing you the acute image, and the blue circles are the Armand raised molecular cloud muscles. So one thing that you can clearly see is that keep in mind that there is a projection effect. This is in 3D, but still the jet clearly bifurcates the star forming regions as well as the molecular clouds. And this is not unique to this particular galaxy. There are other cases like Vygotsky's object or 3C285, where such bifurcation is seen likely induced by a jet activity. So we are probably right in saying that this jet was able to create this particular structure. And along the path, because the jet is quite a lot of energy, the gas is getting heated up, and there is no star formation along the path of jet activity. But away from it, because it is just putting enough pressure to collapse the molecular clouds, the stars get formed, and then molecular clouds also survive away from the path of the jet. And we also looked at how the mass, the molecular mass, and the luminosity of the star forming region change as you move away from this particular jet path. And as you can see, this is the zero separation, and at zero separation almost there is no molecular cloud or star forming regions. But as you move away, you start finding those molecular clouds as well as star forming.
Sorry,
Yeah.
this thing has started.
Oh, I'm done. Actually, I kept it very few slides.
Okay, sorry.
This one. And now I'm going to the inner region, and with this I'll end, of course. So this is again, this is the inner region, and this is the present jet activity. And this is a part of the past jet activity which we found out. Then this is the part of the present jet activity. And now we are just going to look at what happened here. So again, that particular part is zoomed in here. And here what you can see, if it is clear from the back, there is some diffuse structures here. which we will say that it is from hot gas. And there are some point-like sources here, which we are going to look at, say that they're star-forming regions. So just keep the names in mind. A is diffuse emission, B and C are like possible star-forming regions. And in order to confirm them, what we did was, we looked at the Hubble Space Telescope imaging data, archival data, but we only had this F606 wideband filter. And what is important about this wideband filter is that it encompasses the H-alpha line as well. So when we looked at it, we saw lots of point-like sources. And this blue contours are the FUV contours, which we think to be the star-forming regions. And you can see that all those point-like sources align well with the FUV contours. And you might ask, oh, why can't it be just stars from our own galaxy? But then we look at the Gaia data to remove all the foreground sources. And the red points are all the foreground sources. And this is for that particular B region. And this is for the C region, the same region. And then we wanted to find out what's going at A. At A region, we didn't find any point-like sources, but then we look at the Chandra data. You can see this is a color composite showing both soft and hard X-ray emission, and yellow is the soft X-ray emission. So right where we start seeing the diffuse UV emission, we also see soft X-ray emission, and then we argue that this diffuse emission is likely from gas. And that's a summary of it. And I'm not going to go through this. We have done more things in that particular work, which was published in 2022 in MNRAS. You can have a look at it. There are more stuff there. This is just key interesting results. And this is possibly, I will say that we are not confirmed it, but this is jet triggered star formation happening close to the Centaurus. I'll stop there.
So we'll take a quick question.
I didn't hear, but are you asking whether I can say the jet activity is episodic or continuous? Yeah, so this is something always which comes up. So I do not know whether it is an episodic activity or the jet is processing slowly. I do not know.
It's not clear.
Yeah.
We want. Yeah. So the Prime Minister's address has started at 11 o'clock. So it's taking place in the auditorium. So now we're going to go to Ignat Lounge, which is, the INA building at the bottom right, the glass covered building. Okay. So there is tea, coffee, and snacks. If you will have it quickly, I'll go to auditorium to attend the PM lecture. It would be nice, but just a suggestion.